To the eye, the universe is a domain of stars and galaxies, a dazzling pageant of matter and light. But at a deeper level, the universe is governed by unseen forces that rule the fate of every star, planet, and particle of matter that space contains. Among these forces, the force of gravity plays a unique role. Only gravity operates on everything with mass, regardless of its distance, creating a mutual attraction between all the matter in the universe.
From Newton to Einstein, the nature of gravity has preoccupied some of the greatest minds of all time. But beyond sheer fascination, there's another reason why scientists pay attention to gravity. These days, gravity isn't just a force, it's a tool that is allowing us to explore the universe and is showing us what telescopes cannot.
Our gravitational exploration of the cosmos begins close to home. Made up of nearly 6 billion trillion tons of rock and metal, our own planet, Earth, has by far the largest mass and the strongest gravity that humans have ever experienced. In fact, Earth's gravity is strong enough to hold almost anything to its surface, including soil, water, and the very air we breathe. Even the moon, a sister world hundreds of thousands of kilometers away, is held in orbit by Earth's powerful gravitational pull. But Earth's gravity is not uniform. At different points and at different times, it can be slightly stronger or slightly weaker. For scientists, these tiny differences can reveal important information about the layers of rock that lie below Earth's surface, or about the movement of water and ice at the poles and around the globe, all of which have mass and contribute to Earth's overall gravitational pull. And the best way to measure these differences is not from Earth, but from space. This is the Gravity Recovery and Climate Experiment, or GRACE for short. Launched in March of 2002, it's a joint effort by NASA and the German Space Agency to map the subtle variations in Earth's gravitational field 1,000 times more accurately than ever before. GRACE is made up of 2 satellites, which orbit Earth in tandem and communicate with each other using a microwave ranging system. Flying about 220 kilometers apart, they make an exquisitely sensitive gravity meter. Whenever the leading spacecraft passes over a part of Earth where the gravity is a bit stronger, it feels a slight pull, causing it to accelerate and increasing the separation between the 2 spacecraft. Whenever the gravity is a bit weaker, the reverse happens, and the 2 orbiting spacecraft move slightly closer together. By repeatedly measuring these slight changes, GRACE has built up a detailed profile of Earth's gravity and revealed subtle variations across the planet's surface. Here, red represents areas where the gravity is slightly stronger. These correspond to mountain ranges and other large accumulations of mass. Blue shows where there is less mass, and the surface gravity is slightly weaker. Looking elsewhere, GRACE can also record changes that show more directly humanity's growing impact on the planet. In this view of India, red represents a decrease in gravity where groundwater has been drastically depleted by human consumption over the past decade. The quest to measure Earth's gravity with ever greater precision has become a key way to study our planet's hidden structure and monitor its ongoing transformation. But as fruitful as this technology has been, scientists have also come to realize that there are many more places besides Earth where gravity can be an aid to exploration. Now, similar missions are envisioned for other worlds, where we have far less information about what goes on below the surface. The first of these is already underway, and as expected, gravity is providing an exciting new way of seeing what was once hidden. For centuries, astronomers have wondered about the invisible mechanism that seems to keep the moon circling around us with clock-like regularity. It was Isaac Newton who solved the riddle. He was the first to recognize that the same force that causes an apple to fall from a tree is the one that keeps the moon in orbit around the Earth. He not only discovered the law of gravity, he understood it was universal.
5, 4, 3, 2, 1, 0.
More than 300 years later, Newton's mathematical description of gravity is still used to calculate the flight paths of spacecraft that leave the Earth far behind, including those that set out for the moon. In September of 2011, NASA launched not one, but two identical spacecraft, both heading for a lunar rendezvous. This is the Grail mission. Its objective, to use gravity to unlock some of the moon's deepest secrets. Like the Grace mission around Earth, Grail is designed to monitor changes in the separation between two spacecraft as they are pulled in different ways by the gravity of the body they orbit. But compared to Earth, the moon is an even better subject for this double-barreled style of mission. The most important difference is that unlike Earth, the moon has no atmosphere. This means the two Grail satellites can orbit much closer to the moon's surface and, in doing so, make a much more accurate gravity map. At the beginning of 2012, when the two orbiters arrived, they were in highly elliptical orbits that took them more than 8,000 kilometers from the moon's surface, too far for useful measurements. But over the next 8 weeks, those orbits were carefully adjusted into tight circles with an average altitude of just 55 kilometers above the surface. At that height, the two spacecraft were tearing around the moon at 5,000 kilometers per hour, completing one orbit in just under 2 hours. And like a high-definition movie in Fast Forward, the stark lunar landscape rushed by beneath them. Scientists nicknamed the twin Grail satellites Ebb and Flow, because of the shifting nature of the measurements they were designed to make. With flow in the lead and ebb about 100 kilometers behind, they circled the moon in formation so that if one felt a slightly stronger gravitational pull from one part of the moon, the distance between the two orbiters would change slightly. The probes kept track of their relative positions by sending pulses of microwave energy back and forth while maintaining radio contact with Earth. Accurate clocks on board each spacecraft carefully tracked the timing of the microwave pulses, allowing the system to detect a change in the twin orbiters' separation as small as 1/10 of a micron, or roughly half the thickness of a human hair. With this remarkable precision, Grail set out to explore the moon's gravity with 100 times the resolution of any previous mission, 1,000 times for the moon's less explored far side. In this view, the best ever of the far side, the side that always faces away from Earth, we see a rough and mountainous terrain packed with ancient craters. This is entirely different from the moon's near side, which includes large circular basins formed by asteroid impacts. Those basins are obvious on the near side because they are places where darker colored lava from the moon's interior broke through and flooded the surface. But the far side crust is much thicker, which apparently prevented lava from reaching the surface. With its careful measurements of the moon's gravity, Grail can see deeper into the lunar interior and help shed light on why the moon's crust is so lopsided. It may even shed light on a surprising theory based on computer simulations that suggests the moon's thicker far side crust was created in a collision with a second smaller moon. This epic crash would have splattered material all over the far side, like a giant bug hitting a windshield. But there are also deeper questions to answer, including whether the moon has now lost all of its internal heat, or whether deep down it still harbors a small molten core. To probe the moon to such depth requires data from all angles. It takes the moon 1 month to rotate slowly on its axis. So after 3 months of orbiting the moon from pole to pole, Grail gathered enough data to map the moon's entire gravitational field in exquisite detail 3 times over.
Scientists are now continuing to analyze the treasure trove of data that Grail has provided, hoping for a definitive glimpse of the moon's mysterious heart. This is the promise of gravity as a tool for space exploration. It offers a way for us not just to see other worlds, but to feel what's happening inside them.
Not even Isaac Newton could have dreamed of such power. A power that can also help us reach beyond the solar system and explore the cosmos in an entirely new way. For more than half a century, conquering space meant conquering gravity. Gravity was the obstacle that had to be overcome in order to leave our planet behind and travel to the moon and beyond. But even then, scientists knew there was another way to think about gravity, not as a barrier, but as a messenger that can carry information from the distant universe. This idea comes from Albert Einstein. Unlike Newton, who thought of gravity as a force between objects, like an invisible bond, Einstein reimagined gravity as a curve or warp in space. The warp is created by matter, and it also dictates how matter moves. Take Earth, for example. Because it contains a lot of matter, Earth stretches and bends the space around it, forming a kind of dimple in 3 dimensions. As the moon moves, it's guided by the way the space around Earth is curved. Instead of traveling in a straight line, the moon's path follows the curve and keeps circling around us. But this elegant way of thinking about gravity also has an interesting side effect. If space can stretch and bend, then space can also ripple, like a wave, a gravitational wave. According to Einstein, space is full of gravitational waves, like ripples on a pond, created whenever something with mass accelerates. But in practice, these waves are so slight that we don't notice them in everyday life, and we have no means of measuring them as they propagate through space. That is, unless the situation is extreme. And in our universe, there is no situation more extreme than that of a black hole. A black hole is an object with gravity so strong that not even light can escape. Yet even though black holes give off no light, their effect on the space around them can be strong enough to generate gravitational waves. The key is looking for places where black holes are accelerating through space and making big ripples as they go. One such place could be the center of a massive galaxy. It's now thought that most galaxies have giant black holes in their cores. Such a black hole may start small, but as it is fed by the galaxy that surrounds it, it can grow to the mass of 1 billion suns. Many of the largest and brightest galaxies in the universe are thought to have originally formed out of the collisions and mergers of smaller galaxies. If so, such galaxies could host not 1, but 2 giant black holes locked in tight orbits around each other. Because those orbits will eventually lose energy and decay, the black holes are locked in a death spiral, destined to collide. Drawn in by their mutual attraction, the 2 giants whip around each other at high speed. As they do, they generate massive ripples in space. Traveling outward, those waves will eventually sweep through our solar system, carrying information that could help scientists better understand the origin and development of giant black holes and their role in the history of the universe. But how to detect them? The answer is simply to measure space. Scientists have now begun to develop a measuring tool that will use lasers to detect minute changes in length across different distances in space. It's called LISA, the Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft precisely spaced in a triangle that is 5 million kilometers to a side. Using laser beams to track their relative positions, they can detect a change in their separation down to 5 trillionths of a centimeter. Such extraordinary precision lies at the very limits of current technology. But it should be just enough to allow scientists to listen in on a universe that is filled with gravitational waves. What will it be like to perceive such a universe? Most of the time, scientists expect it will be like listening to a continuous buzz made up of waves from millions of black hole pairs located in galaxies scattered in every direction. But every now and then, there should be a much larger boom of gravitational waves created whenever 2 black holes finally collide and merge. It's beyond the ability of even the world's most powerful telescopes to witness such an extreme and violent event. But LISA could give us a front row seat.
Gravitational wave astronomy is so new that in a sense it hasn't even been born. That won't happen until a gravitational wave detector picks up its first real signal. But many researchers expect that moment is coming soon and that our generation will be the first to tune in to a whole new way of perceiving the universe.
As we do, we will again come face to face with a remarkable truth about our universe. Though it often appears vast and incomprehensible to the human mind, contained within its awesome beauty are the clues that will help us understand what makes the universe the way it is. A place where creatures like us can exist and explore.